So what about concavity, and what can it tell us about rates of change? Well, we know the second derivative will measure how the first derivative changes. The greater the magnitude of the concavity, not concerned about whether it's positive or negative, but the greater the magnitude of the concavity, then we know the faster the rate of change changes. So let's have a look at a picture. So on this particular graph, if P was in this position, then we know that the rate of change is positive. It's increasing. But as that point moves further to the right, the steepness of that tangent is going to get less. So therefore, it's increasing at a decreasing rate. This is when the concavity is less than 0. So combine those two together. If the first derivative is positive and the second derivative is negative, then we know that the function is increasing at a decreasing rate. Okay, Q. So it's now moved past the stationary point and it's now going down. So we know it's decreasing. But as Q keeps moving along, that line is going to get steeper and steeper. So when the derivative is negative and the concavity is negative, then it's decreasing, but at an increasing rate. Okay, third situation. It goes past the inflection point, and it's now still decreasing, derivative is less than 0, but now it's concave up. So once it goes past that inflection point, then the slope of that tangent will be getting smaller and smaller. So if it's concave up and decreasing, it will be decreasing at a decreasing rate. It then goes past the stationary point, and now it's increasing again, but it's concave up. So if that point keeps moving, that tangent is going to get steeper and steeper. So when it's increasing and concave up, the function is increasing at an increasing rate. So it's not good enough just to look at the sign of the second derivative. If you have a look at it, when the sign of the first and the second derivative are the same, so that's the two on the right-hand side, then it's at an increasing rate. So the top one's decreasing at an increasing rate, and the bottom one's increasing at an increasing rate. When the sign of the derivative and the second derivative are different, then it's at a decreasing rate. So that's one way of remembering it. If the signs are the same, then it's at an increasing rate. If the signs are different, then it's at a decreasing rate. That, I guess, is similar to what we talked about with acceleration. What we said was when the acceleration is in the same direction as the velocity, we get faster, so at increasing rate. When acceleration was in the opposite direction to velocity, we slowed down, so a decreasing rate. Here's a graph. It's an interesting little graph, and it's showing petrol consumption versus population density. And there's 22 different cities there. Now, when you get less than 20 people per hectare, then people will depend more on their cars for transport, and public transport, there's not a lot of it around. So looking at this graph, what can be concluded about the petrol consumption as population density increases? So as we're moving to the right, what we have here is a graph that is decreasing and is concave up. So they are in opposite directions. Therefore, it's decreasing at a decreasing rate. Opposite directions, slowing down. Here's a temperature graph for Sydney. The question is, how does the temperature change during autumn? Well, at the start of autumn, and autumn begins in March, then the temperature is decreasing at an increasing rate because we have a decreasing curve and it's concave down. They're both negative. So in the same direction, it's getting faster. However, at the end of autumn, so end of autumn, March, April, May. So when, we could look at between at the end of May, start of June. Now it's still decreasing at that point, but now the slope of that tangent is shallower. So it's slowing down, but so it's now at a decreasing rate. Here's one which is, well, topical at the moment, I guess. On March the 22nd, we entered stage 1 shutdown restrictions, and the idea was they wanted to slow down the rate of new cases. Here's the graph that has been put out by the health department of the different new cases, and then the blue curve is cumulative cases. Now we think it takes about 5 to 6 days for symptoms to show up. So the announcement was made on March the 22nd. Question is, do we think that the measure has been effective by all of us staying at home and doing what we have to do? Do we think this measure has been effective? So 22nd of March, 5 days later is the 27th of March. Well, if you have a look at it, it does appear that our curve has inflected. It's changed from concave up to concave down. So whilst they are still increasing, they're now at a decreasing rate because the curve is concave down, but the slope is positive. Different direction, slowing down. So that rate is slowing down, which is what they were trying to do. So, yep, still very early days, but it does appear that these measures have been effective. So 9D we'll look at for this idea of concavity and the rates of change.